Welcome to Forge College. We are currently navigating the Understanding Ethereum's Core Infrastructure module, a key part of our Introduction to Ethereum Architecture course. Today, we're exploring exactly how the physical setup of the network dictates the movement of every transaction. In our last lesson, we looked at the community side of things through GitHub and chat channels. Now we're heading into the machinery of the network itself to solve a common mystery. Have you ever hit send on a transaction and seen it sitting there as pending, only for a friend to check the network and see absolutely nothing? It's as if your digital payment just vanished into thin air. On a regular website, this doesn't happen because everyone is looking at the same central computer. But Ethereum is different. There isn't one single official list of what's happening right now. Sending a transaction on Ethereum is actually like whispering a rumor to the person standing right next to you in a giant, crowded room. As you can see in this network map, that whisper has to travel from person to spread. Because there's no central server, what one computer knows at any given second depends entirely on who it's talking to and which rumors have reached it so far. Every computer on the network has its own private waiting room called a mempool. You can see it here. It's like an internal clipboard where the node stores every unconfirmed rumor it hears. It's important to realize there is no global waiting room. Looking at these three nodes, notice how their clipboards are all different. Each node maintains its own list based only on the whispers it has personally received. When a node hears a new rumor, it doesn't just pass it on blindly. It acts as a gatekeeper, checking for a valid digital signature and making sure there's enough gas to pay for the move. Only the rumors that pass this check get that orange stamp of approval. If a transaction fails this check, it gets tossed out immediately. This is often why a transaction vanishes. It failed the very first security check it encountered, so the rumor never even had a chance to spread. Now, a node doesn't talk to everyone in the room at once. It only gossips with a small group of peers. This map shows peer topology. Notice how the group on the left is tightly connected, while the node on the right is almost isolated. Watch the orange signal. It zips through the dense cluster in a heartbeat, but it takes much longer to reach that isolated node. This delay is what we call latency. This creates moments where the network is out of sync. For a few seconds, one half of the room knows the rumor, while the other half is still completely in the dark. If your connection is slow or you aren't talking to many neighbors, it takes a lot longer for your transaction to reach the validators, who are responsible for locking it into a permanent block. Even if a node hears your transaction perfectly, it might refuse to repeat it. Nodes have policies, acting like a strict bouncer. As you see here, if a transaction has a fee that's too low, the bouncer just diverts it straight into the trash. To save on memory, a node might decide to only listen to high-paying rumors. If your transaction doesn't meet their minimum price, that node will never store it and never pass it on. For developers, the solution to this vanishing act is to use internal diagnostic commands. These are basically status requests that ask a specific node exactly what it has on its clipboard right now. This diagnostic request acts like an X-ray. It returns a snapshot, like the one here, showing every transaction waiting in the pending or queued sections of that specific node's memory. By comparing these snapshots across different nodes, you can see if your transaction is just moving slowly through the crowd, or if it's being blocked by a bouncer's strict fee policy. Let's review the pipeline. A transaction is submitted, survives the node's policy filter, and ripples across the network to a validator. This is crucial. Validators can only pick transactions that reach their personal waiting room. If a rumor doesn't reach them, it isn't recorded. Your experience on Ethereum, how fast your moves are and how fair the network feels, is a direct result of these infrastructure choices, like how nodes filter rumors to save memory. Keep this image of nodes filtering and ordering rumors in your mind. Next lesson, we'll see how this interacts with the account versus UTXO models, where the exact order of those rumors becomes even more important. This video was made by Forge College. To master Ethereum fundamentals and dive deeper into Web3, head over to forge.college and join the conversation.